Welcome to part two of Periodic Trends. It's the follow up to the best selling part one to Periodic Trends. And if you survive part one and you're watching part two, then you have a lot of guts. But let's get through this. So, ionization energy. Before we get to that, let's just remember that an ion is an atom or group of atoms that has a positive or negative charge. And ionization is any process that results in the formation of an ion. And ionization you see in advertising a lot, like an ionizing humidifier, or just to make something sound more scientific than it is so you'll buy it. But what we're interested in is what's called first ionization energy. And that is the energy that is required to remove one electron from a neutral atom. And that's going to be the outermost electron. And let me make sure my pen's working. All right, so my pen's working. So let's take a look at this. So there's our periodic table. So across a period, and when we say across a period, of course, we're meaning from left to right across a period. So ionization energy, well, let's think about this. What happens to the force of attraction as you go across a period? Well, you get an increase in protons, and you have the same number of energy levels across a period. So the force of attraction increases across a period. So if the outermost electron is more strongly attracted to the nucleus, is it going to take more or less energy to remove it? Well, it's going to take more energy to remove it. So across a period, ionization energy increases because the force of attraction increases. All right? So across a period, the electrons are all in the same energy level, but as you move across, the number of protons increases. And the increased force of attraction on the outermost electrons requires more energy to remove them. All right, so let's look down a group. Well, so down a group. So what happens to the force of attraction down a group? Well, we know that down a group, the force of attraction decreases. And why does it decrease? Well, because what's increasing? The distance is increasing between the outermost electron and the nucleus. Because as you go down a group, we just learned atomic radius increases, so the distance increases, so force of attraction goes down. If a force of attraction is down, then it takes less energy to remove it. So down a group, ionization energy decreases. And here's our nice, pretty explanation. As the atoms get larger, the force of attraction on the outermost electron, it should be the outermost electron, is weaker, and it will require less energy to remove it. Sorry, I made some changes on this, and I've made a few grammatical errors, so please learn from my mistakes. Now, metals have a characteristic low ionization energy. It doesn't take a lot of energy to remove an electron from a metal. Nonmetals have high ionization energies. They do not want to lose their electrons. And then the noble gases themselves have very high ionization energies. So let's look at our trend. So we know that going across a period, ionization energy increases. Going down a group, it decreases. So we're looking at sodium. So we're looking at sodium, aluminum, and chlorine. So they're all in the same period. So we know it increases. So chlorine's at the end, so chlorine is going to have the largest ionization energy. All right? So how are we going to explain that? Well, sodium has 3 energy levels. Aluminum has 3. And chlorine has 3. So they all have the same number of energy levels. But once again, if we look at this, if you determine the protons. Chlorine has 18 protons, aluminum has 13 protons, and sodium has 12 protons. So they all have 3 energy levels, but chlorine has more protons, so it has a greater force of attraction between its nucleus and outermost electron, so it takes more energy to remove it. All right, and that's basically what I just said, and there it is written down. So you can write this down. Just pause the video, write it down. I'm going to move on to save time. Oops, I gave you the answer there. Hope you didn't look. So we're looking for the one with the smallest ionization energy. So once again, as we go across, it increases. As we go down a group, it decreases. And you really have to have these trends, just the directions memorized so you can do this. And this time, we're looking, let's see, we're looking at cesium, we're looking at lithium, and we're looking at potassium. So these are all in the same group. Well, what do we know? Cesium has 6 energy levels or shells. Potassium has 4, and lithium has 2. So the distance between the nucleus and the outermost electron is going to be greatest in cesium. So it's going to have the weakest force of attraction. So it will have the smallest ionization energy. It'll take less energy to remove the outermost electrons from cesium than potassium or lithium. So cesium has the smallest ionization energy, and here's our explanation. Now, this is the kind of information that you need to include in a good explanation. So you'll need to pause this and write this down as an example. All right, so we have one more. We're looking at, this time we're looking for the largest ionization energy, and we're looking at oxygen. Titanium is right here, and barium. So look, we know it increases across. We know it decreases as you go down. So we've got oxygen. So basically, if you look, it's not going to be barium, because barium is furthest to the left and it's the furthest down. It's not going to be titanium because it's furthest to the left and furthest down. So the answer is going to be oxygen. So why oxygen? Well, the dominant reason is going to be because oxygen has 2 shells or energy levels. Look, titanium has, 4, and barium has 6 energy levels. All right? So oxygen is going to be the smallest atom. So it's going to have the smallest distance between its nucleus and outermost electron, so the force of attraction is going to be greatest. All right, so there's our answer, is oxygen, and then there's our reason. So copy it down. So this is the kind of information, once again, that you need in your explanation. We need specific numbers and for your scientific explanation for these reasons. So once you pause it, get this written down, and then continue once you have it. And here's just showing ionization energy, how it increases across a period, and you can see it decreases as you go down the groups. And in general, we're looking at first ionization energies. The second ionization energy, like you take a second electron off, it takes more energy for the most part. All right, so we're now going to look at electronegativity. So electronegativity is a measure of the ability of an atom in a chemical compound to attract electrons. And elements that do not form compounds are not assigned electronegativities. So the noble gases, for the most part, do not have electronegativities. So here's the trend. So electronegativity increases across a period. And What's the reason why? Well, if you think of atomic radius, when you go across a period, atomic radius gets smaller. And as the atoms get smaller, there's a greater force of attraction between the nucleus and the shared electrons. And the reason why, remember, across a period, you're increasing the number of protons, the atoms are getting smaller, force of attraction goes up. All right, so that's a little reverse. So down a group, it decreases. So the reason is, as atoms get larger, there's a weaker force of attraction, so electronegativity decreases. So for electronegativity, we're really just going to use the size of the atom to explain it. We know in larger atoms, there's less of a force of attraction going because of the greater distance. And then as we go across a period, you're increasing the number of protons in the nucleus in the same number of energy levels. That's increasing the force of attraction. That pulls the electrons closer so they get smaller, and the distance is smaller. All those add up to increased force of attraction. But you're not gonna have to explain all that as much as just saying in smaller atoms there's a greater force of attraction, so electronegativity increases. In larger atoms, there's less of a force of attraction between the nucleus and shared electrons, so electronegativity goes down. That's going to be our explanation for this. And nonmetals generally have the highest electronegativities, like for instance, fluorine in the upper right corner has the highest electronegativity. Metals have low electronegativities, and francium in the opposite corner has the lowest electronegativity. And here's just a table you can look at that shows that. Like here we have, up here we have fluorine with the highest electronegativity. Here we have francium. Something's happened, we've gone crazy. Here we have francium with the lowest electronegativity. All right, so let's see. Let's circle the one with the largest electronegativity. So we have sodium, aluminum, and chlorine. So look, we know as we go across, ionization energy increases. All of these are in the same period, so chlorine is going to have the largest electronegativity. We also know that of these three, chlorine is the smallest. So the smaller the atom is, the greater the force of attraction between the nucleus and the shared electrons is, so electronegativity goes up. All right? So sodium, aluminum, and chlorine are all in the same period. They all have 3 energy levels. Since chlorine has more protons, it has a greater attraction for the electrons. All right, here's another example. So we have cesium, lithium, and potassium. So they're all in the same group. So lithium has 2 energy levels. Potassium has 4 energy levels. And cesium has 6 energy levels, right? So since cesium has 6 energy levels, it's going to have the smallest electronegativity because there's a weaker force of attraction between its nucleus and shared electrons. And there's our explanation. All right, so let's very quickly in your notes go over valence electrons. So elements in the same group have similar properties because they have the same number of valence electrons. All right, and remember the valence electrons, those are the outermost electrons. They're in the highest energy level of an atom. And these are the electrons that are important because they can be lost, gained, or shared in the formation of chemical compounds. And to figure out, for the main group elements, to figure out how many valence electrons they have, you add up the outermost s and p electrons. So basically, in group 1, we have 1. Group 2, we have 2. We skip the D block, and group 13 has 3, 4, 5, 6, 7, 8, like that. That's the trend for valence electrons. And then very quickly, for ionic radii, this isn't in your notes, but I would like for you to add this to your notes. Please write this down.